Here we will look at the usage of asymptotic notations in equations. So we know that the asymptotic notation, by definition, they are a set of functions, okay? But when we use them in equations, we actually use them to stand for some anonymous function that we do not care to name, okay? So for example, when we say the worst case running time for merge sort, when we use the asymptotic notation and the equation and the recurrence equations, we can write the running time for the input sequence T of n, okay. Actually, there's a typo here. I will fix this in the slide. So it should be 2 here. So the running time of the inputs on the inputs of size n is 2 times the running time of a subsequence, right? Plus the big theta of n. And here the big theta of n stands for some linear function that we do not care to give it a name because it's a linear function, and we know that the cost of combining the 2 sub-arrays is the cost of merging the 2 sorted sub-arrays is in linear running time. Okay, so it simply means that it is the running time of it is 2 times T of n over 2 plus some function f of n, okay? And the f of n is in the set big theta of n, okay? So we don't want to use this as an additional step, and we simply put the big theta of n here. All right, okay? And we can put asymptotic notations on both sides. For example, we say that the big 2 times n squared plus big theta of n, it has the same running time, or it is the same equivalent to the big theta of n squared, because 2 times n squared is a higher order term compared to a linear function. So it also means that no matter how the anonymous function on the left are chosen, there's always a way to choose the anonymous quadratic function on the right to make the equation a valid one. Okay. So there's also a chaining rule applies to the big theta, to the asymptotic notation. So for example, we can combine the linear parts 3 times n plus 1 into a big theta of n, and then we can ignore it and only keep the higher order quadratic term here. All right, so that's how the big theta notations are usually applied or usually used in equations. And next, we're going to see some relational properties of asymptotic notations. So the transitivity rule basically says that if the G of n is the tight bound for f of n, and Hn is a tight bound for G of n, then H of n is also the tight bound for f of n. And it also applies to big O notations. So same applies to big O, big omega, small o, and small omega notations. And when we try to remember the relationship or the meanings of the asymptotic notations, we can use the analogy to when we're comparing real numbers. So the big theta notation is kind of the equal relationship between numbers. When we say fn is big theta of g of n, then we basically mean that f of n and g of n, they grow in a similar speed. So we can use the equal to remember this relationship. And f of n of, if it's a big O of g of n, then big O is the upper bound for f of n. So it's kind of f of n is smaller than g of n. And omega, it's a lower bound, so it's kind of f of n is bigger than g of n. And for the small and the small omega, it's more strict, greater than or equal or less than relationship. So these are quite useful analogies for you to remember how to memorize these relationships. Okay, and some more relational properties. First one is called reflexivity. So if so basically it says that the function is a tight bound for itself, also a lower bound and upper bound for itself. And symmetry, it basically says that if the g of n is a tight bound for f of n, if and this will apply only if and only if g of n, f of n is a tight bound for g of n. Okay? And the transpose symmetry says that, so it's about big O and big omega. So if, so g of n is the upper bound for f of n, if and only if that f of n is the lower bound. So it's quite straightforward relationships. Okay, so in the next video, we're gonna look at some asymptotic bounds for some common functions, which we will see a lot in the running time of algorithms.